Hello everybody and welcome to Amberg TSP Webinar, a series of short online sessions with the final goal of improving your skills using the system Amberg TSP 303 Plus. We would like to thank all of you who are using our system, and we hope you enjoy webinar number 7. As in our previous user webinar, we also invited prospective TSP users to join us. I hope that very soon we will also welcome you in the TSP user community. Please enjoy the session as well. In the session today, we will talk about the new raw data quality check. Before we start the session, let's have a look to the webinar taskbar. If you want to open the webinar attendees panel, you can click on the red arrow button. Please check your speaking settings and change it in case you cannot hear us clearly. In the question panel, you can enter your question during the webinar. We will collect the question and answer them via email. My name is Joseph H. Mendez, and I'm very glad to be your presenter today. So let's start with the content of today's webinar. First, we will have a short introduction about the motivation why we have developed this raw data quality check. Then we will talk about the raw data quality check itself. What is this? And then we will have a look to the analysis that we do in this quality check and what is the scoring system, how it works, followed by some examples. We will do some interaction with the software to see how we apply, how we run this check feature. And then later we will talk of some recommendations, some actions you can do to improve your data quality, and then finalize with some remarks. So if you remember, so let's recap what are the main steps of doing TSP in a tunnel project. So first, what we commonly do is data acquisition. Then we have data processing, and we finalize with the results interpretation in the evaluation set. This table was shown in the first webinar we have ever done. In this table, we just try to, let's say, make an assessment, a qualitative assessment on what is the performance of the user through each of these main steps of doing TSP. We go here through data acquisition, data processing, and data evaluation. If we have a closer look, so we have identified like 9 different situations. Of course, the situation 1 is the ideal one, where we have good data acquisition, good data processing, and good results interpretations. But there are also other situations that can happen. For instance, we should avoid, for instance, situation 3, 4, 7, and 9. You see here where you have, let's say, a poor data processing, data interpretation. This was covered by the previous webinars. So in this webinar, the idea was how can we ensure that the user always get data of good quality, because in this way we are in this situation 1, most probably situation 2 or situation 5 and 6. That's why we develop a way how to quantify this in a more quantitative fashion in order to get a feeling from your data, from your raw data, what is the quality of the data. And the idea is that the users try to get always on this area, let's say, good data quality, even moderate data quality. It will be a good option. We need to avoid this poor data quality. However, let's talk what means data of good quality. What are the characteristics in our data to consider this as a good quality data? So I will show you this with some real data. So we will have now the receiver 1 of one campaign. This is a real campaign. We will look at the component X. It was in the Shorthaul 1. The charge was 40 grams and the maximum amplitude was 3,400 millivolts. Please notice that we have a trace normalization now here with a gain factor of 1. Then let's start to move on the time domain. In this figure now, let me go to the next. Now it should start to move. So we are now traveling in the time domain, the time axis. The first thing you should identify in a good data quality is that before the first break, we have only background noise. You see here very low amplitudes, below 1 milliseconds. This is the first, let's say, feature the data should have. The second important thing is that we can identify the first break easily. We can see it visually very easy. Like in this example, we have noise before the first break, and now we see the first break, which is the arrival of the direct wave. Okay. Then after this first break, we will have the subsequent arrivals of seismic waves. We will start to see that some events are being recorded, are coming from the medium. Now let's move more in the time domain. Now we will look like 120 milliseconds of the data. Now I will change the normalization to the gain to a factor of 20. So I'm magnifying the visualization of the data. What we can see here now is the arrival of the airborne wave. Okay, in most of the cases, we will see this arrival. We are now in the receiver 1. In this case, this receiver was installed in the same tunnel wall as the shot line. But even though in this receiver, we will see also some arrival of the direct wave, but important is that we have a very low to low presence of the airborne wave. In the best case, of course, we should not having this noise of the airborne wave, but this is not always possible because we are in a tunnel and we will have this wave traveling inside the tunnel. So we can identify here the presence of the airborne wave. Now let's move even more. Let's see the entire data set in 500 milliseconds. Now I will show you all the short holes. Now you see here we have the 24 short holes. We are still in a gain of 20 with a factor of 20. And we can still see the low to very low presence of the airborne wave in this red area, in this window I'm showing. Now I will change to receiver 3, the opposite receiver with respect to the shot line. Okay, now we are looking at receiver 3, and now we see, let's say, a little bit more presence of the airborne wave, but please consider this is a gain of 20. Now I will reduce the gain to 1, and you will see that actually is a very low presence of the airborne wave, what we have in this example. Now let's go back to the first milliseconds in this data set. I want to show you then the last important feature for a good data of good quality is the coherency between neighbor traces. If we inspect this data set now, we see here the coherency in the first wavelet. You can see here the polarization, the phases are clearly identified. Also here we see some coherency between the neighbors. Here as well, there is some coherency between the neighbors, and here continuous these events. So in summary, we have only background noise before the first break. We can easily identify the first break. We have the subsequent arrival of seismic waves, very low to low presence of the airborne wave, and then important, the coherency between neighbor traces. Now we have a feeling how should look a data set of good quality. Now let's talk about the raw data quality check, or the abbreviated RDQC. This is a tool for analyzing the signal content in the raw data. Okay, the goal is to classify your data set according to the quality of the data set. For doing that, we just use the raw data, so the seismic traces, raw, non-processed. We will calculate some spectrogram from your data, and then we will push this into an engine, okay, we call the RDQC engine, where we have some statistical, we have also some other analysis, but for the very first time in the software Amberg TSP Plus or Ease, we included now some machine learning techniques. We're exploring now the information in your data to make this kind of classification. And why is this important? Well, it helps us to understand the signal content of the data set and the quality of it. It allows us also to adjust the acquisition parameters or the configuration. We will see that later on. How can we improve or work in the tunnel in order to improve the data quality? And it also gives the processor in the office a first impression of the data quality. This is quite important for the processor. He or she gets this data only looking at this factor, at this check, then he or she will get a good feeling about the data, can make some inference how much time you will need to process this data as well. Let's now have a look at the analysis that are performing this raw data quality check and how works this scoring system. It's an overview. We will not go into the mathematics behind each analysis, but we just want you to understand indeed what are the analysis going on here. So we have first the first break coherency analysis, FB coherency. On this will examine the coherency of the first break between all receivers. For doing that, we will compare some hypothetical regression line. We will find out from your data a representative regression line that correlates all first break, as you can see on this picture. It also has an automatic procedure for detecting outliers. In this case, you can see here that the trace number 11, 13, and 14 are outliers, so they will be not considered further for this analysis. And we will do this for each receiver. So we will get, for each survey, we will get this hypothetical regression line, as you can see here. Now I'm going to receiver 3 and receiver 4. Okay, so we will have 4 of these regression lines. And later on, that comes the analysis itself, we will compare all this, the characteristics of these regression lines. In ideal world, in ideal situation, all of them should be quite similar, but the more difference in terms of the quality of the data, how you install the receivers, the geology, it will start to differ. And we found a way how to quantify how different are between each other. That is exactly what this procedure does, quantifies this difference, find the difference, quantify it, and make a classification out of it. The second analysis we have is what we call the signal to noise amplitude, SNA analysis. This is quite similar to signal to noise ratio calculation. So we will identify first what are the areas within a time window. We define a time window in the data. And we will use this hypothetical regression line that we calculated previously. And then we can now identify 2 big areas. One is the background noise that you have on your data. You see before this first break, and then we will have the area where we have significant signal, okay, the seismic response of the media. And then we can add together these amplitudes. You know, we can sum up these amplitudes on the ratio between the signal and the noise is the value that we get for this analysis, and we will give this classification. The next analysis, on the third and last analysis we have in these procedures, is what we call the signal to noise frequency analysis, SNF analysis. And in this case, we will evaluate the amplitude spectrums of each component in each survey. So we will have, you see now 3 components, 1 receiver. We will have this 12 times, and we will examine this. We will investigate this very in detail with the final idea of identifying first areas where we have the seismic signal and is consistent in all receivers in all spectrum. Okay, areas where we have the airborne wave noise. You remember that from the time Fahrenheit code we use this, so we will identify this airborne wave noise. On what is outside from these 2 major groups will consist of the background noise plus other noise if existing in the data. So this is basically the signal to noise frequency analysis. And now let's have a look how we make the scoring of this. I think there is one comment I need to check. Oh, okay. We will see the scoring of this analysis and how works the classification. So the first score I will show you now is the first break currency analysis scoring. And what you can see here is we have a points to a scoring system in a step of 2. Okay, you can get is varying from 0 to 6, where 0 will mean it fails. It may happen that the analysis fails, and it will then assign 0 points. If it gets 1 to 2 points, then we have a poor data, poor classification. 3 to 4 is moderate, and 5 to 6 is good data. This is only for the first break currency analysis. For the signal to noise amplitude analysis, we use similarly, but now we have only one point steps. So you can get 0, it will be a poor data set or a poor classification in this case. 1 is moderate, 2 is good. And finally, for the signal to noise frequency analysis, we use 2-step scoring system, varying from 0 to 4. Okay, this is the scoring for each individual analysis, but now we will add this together. We will add these scores in order to obtain a total score with just summarize all the analysis. On this will be what you see in this total score, the classification that represent the quality of the entire data set. This will vary between 0 and 12 points. And now you see we have a more, let's say, discriminate classification, varying from very poor up to very good. And of course, our idea is that we get values always from, let's say, moderate good to very good data. That is the goal, let's say. If we look this closely, you will realize that the first break currency analysis is the one which apports more to this total score, since it's going from 0 to 6, followed by the signal to noise frequency analysis, adding up to 4 points. And then the less weight, let's say like this, is the one coming from the signal to noise amplitude analysis. So this is what you will get then, a total score which will classify your entire data set. Let's now have a look how we use this in the software. The example I will show you now is using the software Amberg TSP Ease acquisition. This is the place where you run the raw data quality check. And now you see here we're in the shot number 24. And you see here at the Shorthaul 24. So this is the complete. You have finished 24 blasts. You have the entire data set. And now let's have a look here. These are the 4 receivers, each component, so 3 components. So we have 12 traces. We are looking now at the last shot number 24. Now I will change to the receiver gather, where we have all 24 shot holes for one receiver. We're looking at the X component of receiver 1. We'll do some zoom here. Now we can see the data. When you see now this characteristic, you start to see why is this a data set of good quality. Sorry if I didn't mention this first example is a good data, a data set with good quality. And now we can start to see why this will be classified as a good data set. This is real data, by the way. You see here down the first breaks. And now if you want to run the raw data quality check, you need to go back to the campaign management. For doing that, you will see I went up. There is these tabs on the top. You can click on this tab, campaign management. You go directly to this window. If not, you can go in the bottom below, go back until you get to the campaign management. Now I click on it. And now we are in the campaign management window. Okay, in this window, you see here you have the raw data quality check button. In the left-hand side, we have information about the campaign. You see here the RDQC, and it has not been classified because it has not been run. So I go here, and I will click on this button, and I now in the window of the raw data quality check. Oh, sorry, there was a problem here. This may happen. Okay, now here, raw data quality check. As again, the description. Just jump back the video, sorry. Now you click here. Now we are in this window. You see there in the left-hand side, you see that there are no results available. Please run raw data quality check. And for running it, you go down. Now here down, and then you click on it. And now the process is started. That's all you have to do. You click on it, and now you have all the three analyses going on in the background. It will take less than 1 minute, and then we will get the results. Should be about to finish now. Now there are the results. Above is information in this area. 24 shots were analyzed, and now we have the analysis here. The first analysis got 6 out of 6 points. The signal to noise amplitude analysis 2 out of 2. And the last got 3 out of 4 points. The total score now is 11 out of 12. This corresponds to a good classification, a good data set. And now here we see some description. Let's read this. The raw data quality can be improved. Data processing will achieve reliable results. The full prediction distance will be reached, and the prediction accuracy will be good. Of course, we have a good data set, should be like this. But now on this side, you can see here with some recommendations. This is a list of things you can do in order to improve your data quality. Now it's a short list because we have a good data set. If we go now back to the campaign management, you will see now there is a stamp. Now here, this summarizes the quality of the data. I will go back to the raw data quality check. And always you can go here to the data viewer. If you click on this eye, on here you can then, let's say, corroborate again, see your data, analyze it, and you will see, okay, it corresponds to a good data set. Okay, this consistency, the output from this analysis. That's it for a good data set. I will show you now briefly how looks the other traces in the other surveys. We have receiver 1, receiver 2, receiver 3, and 4. I'm showing only the component X and Y. And now we can see, so more or less here the first trace, we see there is no background noise before each first break. We see that the coherency between the traces is important. We see in the component X also there is a nice coherency between neighbor traces. We see some events here. So the data set looks quite good, and that's why it got this classification as good, this high point. Let's now have a look to a data set classified as 4. Okay, let's see this data set as an example. Now you see here we are in the shot number 31 at the shot hole 24. So this means in this case the people in the tunnel was repeating some shots. There were some troubles during the data acquisition, maybe collapsing some shot hole, maybe some misfires. So they need to repeat at some shot holes the recording. Now let's look at the data, the 12 traces. I will change, I'm going a little bit faster here. Let's look at these first milliseconds of this data set. And now you start to see there are some first play you can identify, but also you can see here on the top some noise, some misfires here. So it doesn't look that good as the previous one. And now we go to the campaign management again to run the data quality check. You see, it has not been run. Then we go click on this button here, and now we can start the raw data quality check. As I said, in the computer, in the notebook delivered with the system, it should take less than 1 minute as well. Of course, the data large, if you have 2 shot lines, it will take maybe a little bit more time, but it's a very fast procedure. Now you see the results here. Analyzed shot. Now we see that there are some jumps here, so maybe there was some collapse in this. They have to jump some shots. And now we see the classification here for all. We have poor, on the total score for this data set, you see is, oh, sorry, there was my window here, is 12. And now we can see the description is poor here. And now we see the description. The quality of the raw data needs to be improved. It is very likely that the data processing will not produce reliable results. The prediction distance and accuracy are reduced. If we go to the recommendation, now we have a longer list. You see, now for this case, you need to read this, go through each of this step on try to improve for the next campaign. If we go back to the campaign management, now we see the stamp here. So it has been run. You are sure about that. And now you can export your campaign, send it to the people doing processing. Let's look at summary again, similarly as before, all the receivers here, component X and Y. And we can see here that there are some misfires in all receivers. We see some burst noise here, it could be anthropogenic noise for any reason. Maybe a hammer was working, a jumbo was working somewhere. We see here receiver 4 has a very, very low signal to noise ratio. We see in the Y component of receiver 1 some really bad coupling of this receiver. Only receiver 2 looks, let's say, acceptable. That's why it gets some points of the first break analysis, but it's still, this is a poor data set, need to be processed very carefully. You saw already in this window where we run the raw data quality check, there was some general description. I read this for you before for the good data sets and the poor data set. And these are some preliminary insights on should I improve my data. Of course, if I have a poor data set, you need to improve the data for the next campaign. For this campaign is over, but you get a feeling if you are doing a good job or not. If not, then there's these recommendations. Or the other things you can get from this general description is the reliability after processing of the entire result on the achievable prediction range. These are preliminary insights. It will depend on how good we do the processing, on if we can extract enough significant data that we can even get more reliable results or even keep the prediction range. That's why it is called like preliminary insights on the tunnel side. The other thing you saw was on the right-hand side was this window with the recommendations. On this is a list of actions that you can do in order to improve the data quality. This can refer to different actions you can do, is checking some components, making some adjustment, improving the way you're working on the tunnel, and doing some replacements. I will show you now some of these actions. What means some of these recommendations, just selected ones because sometimes it can be a long list. The first one is regarding to hardware. For instance, we get this data set. You see now receiver 4, the 3 components of receiver 4, okay? And we see that in this receiver, we have these peak signals, periodic, repeating at some times, and this is some undefined noise. This peak signal are not normal. This is some undefined noise, and in this case, we know this by experience. This can be a problem with the sensor or with the cables. Okay, so when you get something like this, it will, of course, has an impact on the classification done by this raw data quality check analysis, and then we will recommend you to check in the office after that campaign, go into the office and check careful all the cables by doing a in-office test of the entire system and find out if there is something going wrong with the cables or the sensor. Other situation is the receiver and shorthaul setup. For instance, you see here, this is in the Amberg acquisition software. The receivers in this, the user in this case says, okay, receiver 1 and 2 are on the right-hand side of the tunnel wall, receiver 3 and 4 on the left. But I will show you now, the actual layout in tunnel was the receiver 1 and 3 were on the left-hand side, on the receiver 2 and 4 on the right. So there was a problem here while the user was assigning the position of the receiver. she or he made a mistake. Okay, this may happen, but of course, this will have an influence on the calculation we are doing in the raw data quality check. So if you need to check, or you need to ensure that this assignment is properly done in the tunnel. Another important aspect is the shot hole and detonation depth. Okay, in this cross section, you see this is my tunnel now. We have the EDC, the excavated damage zone. This is the fresh rock. The idea of this shot hole 1.5 meters is that we are able to introduce explosive charge to the bottom of this shot hole. Okay, make ensure that this is in the bottom and ensure that the explosion is occurring there. And now let's imagine we are in a very fractured rock, a very bad rock condition. In this case, the EDC will be larger. And in such situation, a good recommendation will be, okay, I will do that. I know my geology, my lithology is quite fractured, quite bad geology, bad rock condition, and then you can use instead of 1.5 meter, you can use 1.8 meter depth, and in this way you go even behind this excavated damage zone, and the energy will be transmitted in this let's say fresh rock, even if fracture. So these are some recommendations you can follow to improve the data quality. Another very important aspect is the receiver installation. I show you these two pictures now. You see here, in this case, almost one third of the receiver is out from the receiver hole. The question here will be, did they reach the total depth, or maybe it was too short? Maybe the seismon got stuck in the way, but definitely this is not a good situation. We should try always to reach the 2 meter depth, that the sensor is 2 meter depth on the rock mass. Here you see that the sensor was installed in a fracture, and of course in this way you cannot guarantee a good coupling of the sensor with the rock mass. Another way to realize if you have done a good job, when you retrieve the receiver, this may not happen. The dowel must remains inside the the receiver hole. If this happens, this means that the dowel was never tied to the rock mass with the seismon. So this is a good way to check if you have installed very good your receivers. Now I'll show you a picture where we see two well-installed receivers with a very nice depth, and hopefully the dowel remains inside when they retrieve this. Another important aspect is the detonators times, the triggering times, or misfires. If you have some misfires like here, shot 4 on 5, 18, 15, these are some misfire. Okay, so the recording started too late because problem with the receiver, with the detonators. Also, we see here some instabilities. These are not uniform. And this may be due to the detonators quality. If you are using non-electrical detonators, you're using the wire brake, you need to ensure that this wire brake cable is always in this position. It's not like one time is here, one time is here, one time is here. This will cause this variation in the first brake times arrivals. If you are using electrical detonator, it's a little bit more complicated because it will depend on the quality of the blasting machine. The blasting machine in some cases also, so if it's very old, it will have less accuracy in the triggering times, and also it has some dependencies on temperature, on humidity. Explosive and blasting, this is also important. So explosive, we recommend always to use detonation velocities higher than 6,000 meters per second or 5,000 meters per second. Also, it's important to have small charges. If you use, let's say you need to increase the grammage you are using, you can do that, but try to ensure that this is short, not like 50 centimeters of explosive. You need to simulate a point source. That's the idea, keep it this tight. And the other important thing is to push it down to the borehole. You see here, there is putting completely down. There is a mark 1.5 meters on this road. And he pushed this completely down. The most important thing here is to tamp very well, to do a good tamping of the charge. In this case, we're using water, and you need to saturate the short holes with water. Okay, this is quite important because this minimizes the presence of the airborne wave I showed you in the previous example. And finally, I will talk about the rock mass condition very shortly. You see here, this is a shear zone somewhere in the tunnel. Let's say the face is here, and we have here some fractures. On this, to locate the receivers here will not be a good idea at all, because this will bend too much the travel path of the waves, and it will absorb a lot of energy. In this situation, I will recommend go further with your tunnel, and then you can locate your receivers in another place where you avoid such situation between receivers or between shots and receivers, whenever possible, of course. These are some actions on the tunnel side. Now I will briefly mention how it looks the raw data quality check in the Amberg TSP Ease processing software in the office side. Here you will have also some recommendations. And now the recommendations are related to, should I use default processing? Should I carefully check my processing parameters? About also the results reliability on the achievable prediction range. You see here the two examples that of good quality, that of poor quality they get also in the office, the entire scoring system. In addition, there are some details here. You can click on this on the office software, and then you will get some detailed information about different warnings or recommendations you should follow for doing processing. For instance, warnings about using all traces. Maybe you should not use all traces, or you should not use all receivers. Check geometry, check data, raw data carefully, polarity issues maybe, on careful adjustment of processing parameters, the filter setting, the Q filtering. If you have a poor quality data set, for sure you need to do this more manually on some interactions in each processing step. With this, we are coming to the end of this webinar. I will mention some final remarks. So with the raw data quality check, now we have a quality assurance tool. We found a way how to quantify the quality of the data and make a classification out of it. With this, you can improve. You can see I'm doing a good job on the tunnel side, and then for the next campaign, you try to follow the recommendations in order to get data of good quality or very good quality, even moderate good quality. It's okay. This is important. The raw data quality check can only be executed in the Amberg TSP Ease acquisition software. You need to run it there before you send the data to the office for processing. This tool is available since the version 1.2.10 10,460. It was released in February this year, and you need to update your license. So in case you haven't done it, contact your local dealer or contact us directly to update your license. And at the moment, the raw data quality check is only available for data recorded by the single shot recording procedure. With this, we are coming to the end of this session today. Thanks everybody for attending this webinar. I hope you like this new tool. Please start to use it as soon as possible. We hope to see you soon in one of our future events, and also maybe in the next working site. Please stay healthy, have a nice day, and see you soon. Bye-bye.